Awesome. Hello, everyone. We are super excited to kick off our second keynote address for JuliaCon 2020. We are joined by Juan Pablo Vielma. Juan Pablo Vielma was previously a associate professor in operations research and statistics at the MIT Sloan School of Management, but he just informed me he is currently in a new position as a research scientist at Google. And Juan Pablo is also one of the key contributors to the JuMP.jl package. So Juan Pablo, kick it away.
Thank you very much. So it's really exciting to be giving the keynote. It's actually my first keynote and my first online presentation. So hopefully it will go well. So, and what I want to talk about is basically conic optimization in Julia and JuMP. And so basically, I guess the easiest way to know what conic optimization in JuMP is by going to the JuMP tutorials and clicking on the conic programming notebook. And you'll find the first example is a very simple optimization problem that's trying to find, basically project a point onto a hyperplane. And this is how you would write it in math, but it tells you, well, if you want to write it in JuMP, you actually need to do a little bit more work. And basically, instead of just working directly with the norm, you need to work with the cone or the epigraph of the norm function, which is the Lorentz cone or the ice cream cone that you have right here. And if you look at the JuMP code, it basically looks very similar to the math here. You need to write down, instead of writing down a norm in the objective, you're writing some vector that has to, you're asking it to belong on the second order cone, which is again, this ice cream cone over here. So one of the things I want to talk about is like, well, why are we doing this? Why couldn't we just write down something with norms? Couldn't we just use the nonlinear interface in JuMP? And you can still do that, but you could actually get a little bit of extra power by doing the conic formulation using this particular form. So I want to talk a little bit about is like, why is it that this conic formulation is more interesting? How did it become one of the most important ways of writing optimization problems in the current versions of JuMP? And in particular, one of the solvers that was very focused on conic optimization was the Pajarito solver. And it currently only works on JuMP below version 0.18. So I also want to mention, like, why is it that this hasn't changed yet? There's going to be a lot of like mathematical details that I won't have a lot of time to cover. So I'm trying to put links to everything, to notebooks and tutorials like the JuMP tutorials everywhere through the slides. So, and I'll share the slides later in case you cannot copy the links. So going back, what is conic optimization and how is conic optimization handled in JuMP? And again, in the conic programming notebook in the JuMP tutorials, it explains that a conic optimization problem is this optimization problem that's written as maximizing some linear function over many of these conic constraints. And the generic form is you have some affine function of the variables and you're asking it to belong to a given cone. So it could be the Lorentz cone that I showed over here, and there's a lot of extra cones that you can have. In particular, one cone that is actually very powerful and useful is the cone of all positive semi-definite matrices. And if you use that cone, you could, for instance, write down a very, very simple optimization problem in JuMP that tries to find the largest eigenvalue of a symmetric matrix by just writing down the constraint of this given matrix is in the positive semi-definite cone. So this is a little bit of a, I guess it's like a toy example, doesn't really show you what you can do with conic optimization. So let me start with a little bit more interesting example. And this is an example that I've been using for a while, since the beginning of Pajarito.jl, basically. And this example is actually slightly more. So it's a conic optimization problem, but in addition to the constraints that I'm allowing you to use here, I'm going to allow having extra constraints that say some of these variables are going to be integer. And that's going to give us a little bit more modeling power to be able to like build a little bit more interesting problems. And the problem that I'm looking at is basically the control of a drone, so some automated drone. And I want to control this drone so that it avoids some obstacles that are shown here in blue. And the way that I'm going to describe the trajectory of this drone, I'm thinking it just in 2 dimensions. It's going to be its position with respect to time. And I'm going to expect that the position is going to be a function of time, some continuous function of time. It could be a polynomial, but the polynomial won't give us enough freedom to be able to add avoid the obstacles. So I'm going to go a little bit further, and I'm going to sort of discretize this by saying I'm going to divide the time period. I'm assuming the time period goes from 0 to 1. I'm going to discretize it in it's separated into some intervals, and in each interval and each sub-interval, I'm going to request that the position as a function of time is a polynomial on t. Okay, so that's going to give me a lot of freedom on how do I actually describe the trajectory. I'm going to easily be able to restrict the derivatives and things like that. But in addition, by doing it piecewise, I can actually incorporate discreteness to try to avoid the obstacles. And the idea is very simple. Instead of trying to avoid the obstacles, I'm going to delineate these green boxes that could be boxes, but could be general polyhedrons, which are places that I know are safe. As long as I'm strictly contained in one of these boxes, I'm not going to run into any of the blue regions. So my safe constraint will be, well, for each one of the intervals, whatever polynomial you're using to describe the trajectory in that interval, that whole polynomial has to be contained, that whole trajectory has to be contained inside of one of the boxes. I don't care what box it is, but it has to be at least one of the boxes and only one. So this constraint is looks sort of complicated. I'm asking for a polynomial to be inside a box, but I can transform that and realize that, well, if I basically put the polynomial inside the polyhedron, multiply things around, my constraint is going to look like some polynomial in t, slightly different, needs to be greater than or equal than 0. So it still looks very infinite dimensional. It's kind of hard to work with, but there's a technique known as sum of squares, which basically tells you that if you want this polynomial to be non-negative in the interval, you basically can ask it to be, it's nearly equivalent to asking for it to be a sum of squares of some other polynomials. And if I go and restrict the degree of the polynomials, I can write down this with several extra variables and make it so that it's a semi-definite constraint like the simple one I described over here. So, and there was a lot of math here. So here's some links that explain more details on how do I get to that. But basically, I got through sum of squares to write down this problem as a mixed integer semi-definite perming problem that Pajarito could have solved. And these are some results that Joey ran back in 2017. And basically he used JuMP to basically write down a polynomial optimization problem, sum of squares.jl, transform that into SDP, and then we can solve it with the MISDP solver Pajarito. And you could do interesting things like make the avoidance problem while making somewhat of a smooth trajectory, or you could do even like more fun things like it's like Joey called it the helicopter problem, and I was thinking it kind of looks more like the Flappy Bird problem, where the dynamics makes it so that the point wants to drop, and every time you click, you basically give it a boost up, and you can try to say minimize the number of clicks that you need to be able to solve this. And even back then in 2017, it solved fairly fast, even though it was like a complicated mixed integer problem. So for that, there was, as I mentioned, there was a lot of links that you needed, that potentially needed to follow to understand all the steps of the math. The interesting thing is that, well, you might not even need to really learn all the Conic optimization steps that I'm giving you, because if you look at the JuMP code for modeling this, you'll see that basically it's defining polynomials and writing the constraints in a way that looks sort of how you would write the math. And in no place you see Conic explicitly. So JuMP.jl and sum of squares.jl will make all the transformations to make it work. So you could try it without necessarily having to understand every single one of the steps. And in addition, if you actually want something that looks more like expression or NLP-based modeling, there's a technique or a modeling technique called disciplined convex programming that allows you to follow some simple rules, and it will do the automatic transformation for you to a Conic form as well. And that's available through convex.jl in the Julia environment. Now, still, so one of the things I like about Julia is you can start playing with it and try it, and then you can sort of like start peeling the onion and kind of know what, well, I'd like to know more what is behind and why this thing is working. So let me tell you a little bit about that. So the first question is like, well, why Conic? Why do I go with the complication of writing a Conic problem instead of just using functions or expressions? And one of the most interesting things is duality. If you write down a general nonlinear optimization problem, you can have Lagrangian duality. somewhat you can interpret it, but not that easy to understand the sort of like an intuitive meaning of what this primal dual pair looks like. But for conic optimization, the primal dual looks almost exactly the same as what you would have in linear optimization or linear programming. And again, you can see it in the Conic programming notebook. And the very nice thing is that it allows you sort of an explanation of what are the limits that actually to optimality. Why can't I actually maximize or minimize this more? So you get things, you could get things that look like max flow min cut theorem or Mengen theorems that will allow you to understand what are the blockers to get something more out of your optimization problem. And in particular in polynomial optimization, it has some very interesting connection to measures, and you get go slightly further with things that look more closer to what JuMP will do. So instead of just cones, you could also have like a slightly more complicated sets. And if you want to know more about that, actually, the great thing is like Benoit Legat, who's one of the core developers for JuMP, recently graduated. So congratulations to Benoit. And you can actually learn a lot more about this duality and geometric interpretations of duality on his PhD thesis that you can find in his webpage. So it's nice from an interpretability perspective, but you could actually go a little bit even further. And one of the reasons conic duality is useful is for actual algorithms. It immediately improves it allows for more complicated or more effective interior point algorithms for conic optimization. And I'll talk a little bit about that later. And in particular, this is one of the reasons in 2018, there was a little bit of a shift from some of the more important commercial solvers for continuous optimization. And they basically switched to a more conic centric point of view. So Nitro, for instance, added support for second order cone constraints. And Mosaic basically deprecated all the expression or function-based formulations and focus purely on conic optimization. And in particular with a small number of cones, but this small number of cones is basically enough to almost model whatever you would want to model. So, and the reason they did this is because it actually, it makes the solvers more stable and allows you to actually get much faster solvers. So, and this whole sort of shift from conic has been very tied to sort of the history of how JuMP's been evolving. So for the first JuMP developers workshop we had in Cambridge, the first two talks were basically Miles was telling us about JuMP and MathProc Base, which is sort of the back end of JuMP at the time. And then we had Chris that was telling us basically how Pajarito actually uses and connects to MathProc Base to actually make everything work. Interesting enough, the next day we had Benoit telling us about sum of squares, which was one of the first places I kind of saw the interesting or the potential for these type of modeling paradigm. And interesting enough, I guess we were already ahead of our times. That was a remote presentation that Benoit gave at the workshop. And I would say here is exactly where sort of the shift to conic potentially started with the conversations of the people that were there. And the following year in 2018, in the second workshop, we see that it actually had a lot to do with conic optimization. Math op interface was introduced as the new backend to JuMP, which was very centered to things that look like conic optimization or even generalizations. Benoit introduced or was presenting about reformulation of these problems using constrained bridges, which is a key that actually makes it easy. You don't need to worry too much about what cones you have available, the solver has available. And we had a lot of, we had people from the actual two solvers that I mentioned, and a lot of applications and solvers related to conic optimization. And well, and MathOpt interface introduced a new sort of something that looks very similar to this, a find function that belongs to a cone, but slightly more general, is like function in a set that includes the conic paradigm, but also includes a little bit more. And in particular, currently MathOpt interface function in set approach allows a whole bunch of different types of cones, including I guess if I find it, the second order cone is around here, positive semi-definite is around here, and you have a lot of extra cones, and there's a few extra sets that you could have that are not necessarily conic, but MathOpt interface will also understand. So great, basically the thing that Pajarito was waiting, the reason Pajarito worked on the before 0.18 is because it was connected to MathProc base. Pajarito would need to be updated to MathOp interface. So basically it would just be a matter of doing that. But there was one question about, or a couple of questions about Pajarito, where it's like, is it Julia based? And it's mostly Julia based, but it also needs to call a mixed integer linear programming solver and a continuous solver. And at that point, both of these would be calling external solvers that were not written in Julia. And in particular, one of the solvers we relied heavily to make Pajarito work well was actually using Mosaic as a conic interior point solver, as a conic continuous solver. And Mosaic is extremely stable and really good. Pajarito would probably not be as effective without it. But it's not written in Julia. And the other thing is that it only uses the standard cones. So cones that are sort of like a small number of cones that through the bridges can model everything else that MOI can model, but you need to add formulations that potentially are more complicated. And I'm going to give you a precise example in a few slides. So I guess after the last meeting, the JuMP dev, the second JuMP dev, Chris, around July 2018, was like, well, what about making a pure Julia-based continuous solver that doesn't need to do the reformulations, that directly deals with all the cones that MOI could deal with and more. And so I would say these was like a chicken and egg thing on adding more cones directly to MathOp interface was part of like happening all at the same time. And of course, I'm not an expert on continuous optimization. Chris was not an expert on continuous optimization, but Julia makes you bold. So let's just do it. And we started working on that. And basically that's Chris got started on Hypatia. And Chris named it Hypatia because Hypatia was I guess a Greek Egyptian mathematician who liked conic sections and actually designed an astrolabe, which is technically an analog computer. So she likes computers and cones. Perfect name for a conic optimization solver. And we started working over the years. So then Leah Kapelovich also joined the team and started working on this. Some of the first presentations on this happened on the third JuMP Dev workshop, which happened in Santiago last March. And I would say at this stage, Conic was sort of like very centered on what was being done in the JuMP world. So again, there's these two talks that were directly related to Hypatia. So I also want to mention a few more. There were more, but one of the interesting ones is Tulip.jl, which is an interior point solver only for linear optimization that uses a lot of interesting features from Julia using abstract linear algebra, for instance. And perhaps one of the interesting things about this solver is that it's the only pure Julia solver, as far as I know, that has been included in the classical optimization benchmarks by H. Middleman. So that's an interesting thing. It's competing with LP solvers or AP codes that are written in C or more classical languages. Then Benoit also introduced a lot about the set programming stuff that actually is on his thesis. And another thing that I wanted to mention is Julia Moments, which basically is the dual of the sum of squares and gives an interesting moment measure interpretation to polynomial optimization. That again, if you go to Benoit's thesis, you can learn a lot more about that. So in the, so I remember how much time I have. So I guess in the last few minutes, I wanted to actually tell you, I'll dive a little bit deeper on what Hypatia is doing and what conic optimization, like what the interesting things you could do with conic optimization inside Julia. And I'm going to go, basically one of the things I want to talk about in detail is barriers, because I think there's an interesting potential there for extra development. But I'm going to go sort of like high level. And again, if you want more details, we have a paper that will explain this, and hopefully there'll be more, Hypatia will be released soon. So there'll be more interesting, more details there. And so what is Hypatia? It's an interior point solver. It's based on, it's a homogeneous interior point solver. So it's based on an object called the homogeneous self-dual embedding. And it works for standard cones or also more exotic cones. So standard cones like semi-definite programming, or basically all the cones that Mosaic can work with. And in addition, it could do things like The sum of squares is actually a cone. You could tackle the sum of squares cone directly without needing to go through the semi-definite cone. And you could do even slightly more crazier versions of the sum of squares cone. So a matrix of where each entry is a polynomial that is a sum of squares of other polynomials. And these kind of objects you can use to, for instance, restrict the trajectory that I had before to be convex, or add other types of shape constraints to trajectories. And it has about 24 predefined cones that a Hypatia can deal with directly. So like slightly more like going beyond what like is currently directly accessible from MOI. And in addition, it allows you to actually add a new cone. So if there's a new cone that was not included, you could bring it. And the main question is, well, how do I add a new cone? And the way to add a new cone is through an object called the barrier for the cone. And I'm going to discuss that in the next slide. And by having this wide number of cones and potentially additional cones, you can take advantage and basically write down formulations that are much smaller, will take less memory, and potentially will give you a computational advantage on solve time. And there's a lot of extra interesting things in Hypatia as well related to Julia. So it made it very easy to add multi-precision arithmetic, to use abstract linear operators. So if we needed to do things that were sparse matrices or very structured operators that actually could potentially give you a big advantage, easily switching from direct solvers to indirect solvers and things like that. That unfortunately, I guess I won't have too much time to cover. So, but I said barriers. So the key for interior point work algorithms for conic optimization to work well is in part the strong theory of barriers for conic optimization. I mentioned the homogeneous self-dual embedding that I skipped, but basically one of the keys is if you pick your primal dual pair, after some transformations, you can basically deduce that solving the optimization problem is equivalent to following a dynamical system that's described over here. And this dynamical system basically has some linear equations, some nonlinear equations, and some extra constraints that end up being not too terrible, because if you actually focus on these and started in a place that was a good place, following this trajectory closely will keep you inside these constraints. So this is linear. So the key is basically what are these nonlinear constraints? And these nonlinear constraints or nonlinear equations are based on, you get one for each one of the cones you're considering in your formulation. And this G function is basically the gradient of a barrier for the cone. So I'll read the long name in a second. Let me maybe show an example. So for instance, if I want to look at the set or the cone, which is the non-negative ray, let's say for dimension 1, it's basically minus log of x. And you can see that basically what it's doing is it's finite valued inside the set. And the closer you get to the boundary, it shoots up to infinity and doesn't allow you to actually leave the set. And so that's why it's a barrier. But in addition, it has a lot of extra properties. It's a logarithmically homogeneous self-concordant barrier. And I won't go over the details of what it means, but it gives you a lot of theory and a lot of properties that you can exploit on the interior point algorithm. And it could be as simple as minus log of x for the non-negative ray. If you have a slightly more complicated cone like the log determinant cone, you get a slightly more complicated barrier. But the key is, if you want to introduce a new cone, the only thing you need to do is figure out what the barrier is, a logarithmically homogeneous self-concordant barrier, for that cone is. And this could be an expression, it could be a function, it could be a Julia function. It could actually be Julia code. It could be as complicated as you want, as long as you can give that Julia code for the barrier and you check that in fact all the necessary properties worked, you can plug it into Hypatia and Hypatia will be able to use it. And in particular, if you just plug the function, Hypatia could use automatic differentiation to actually get the gradient. For some of the cones, we actually use that at first. Then we kind of tweak for some of them, we tweak them to improve a little bit more the performance. But again, even if this was not an expression, it was a complicated Julia function, you could just plug it in and Hypatia will use the AD tools inside Julia to basically calculate the gradients and do the appropriate discretization of the dynamical system. Why do I care about having more cones? I mentioned that more cones allow you to do more natural models, or at least more smaller models. So let me show you only one example. So this is a problem called the optimal experimental design. And basically what it's trying to do is trying to design a linear regression experiment that will give you a predictor that has the minimum variance. And you can recognize something here that looks sort of like a Fisher information matrix. And what this problem is trying to do is basically trying to minimize some function of the eigenvalues of the matrix. So let's say a function of the determinant would be the product of the eigenvalues. So we're basically, this function is ends up being the covariance matrix of the estimator that you're designing, or the regression experiment that you're designing. And so this is what you would write sort of like in math. And if you want to write it in conic form, you basically just need to use the log-det cone square from MOI, and you get a formulation that looks almost exactly as the one you wrote at the beginning. Now, this requires actually using the log-det cone square. So if you actually, that is not available directly in MOSIC. So if you wanted to use MOSIC directly to solve this problem, MOSIC understands the semi-definite cone and the exponential cone. You can rewrite this problem for those cones by adding extra variables, extra matrix variables, and writing all this. And this is basically something that the bridges in JuMP and MOI will do automatically for you if you actually need to. The only problem is that you added these extra variables, and now you have a problem that is significantly larger. And this could actually cost you in memory, in speed, and in solvability in general. So here's some experiments that are slightly outdated on Hypatia, but still kind of give you the general idea of what's the power of having these slightly smaller formulations here. And here we're comparing Hypatia solving this smaller formulation, Hypatia solving the big formulation that would have been constructed through the bridges, for instance, and MOSIC solving the formulation that it can actually, again, it's the same one, but it's the only one that it cannot go directly. MOSIC would not be able to solve the natural formulation directly. And we can see that I was actually quite pleased that Hypatia could get this close to MOSIC on the same problems, because MOSIC is extremely advanced and has a lot of improvements that Hypatia doesn't have. So we got close. Of course, we couldn't win, but if we could actually solve a much smaller problem, now we had an advantage, and we could actually do a lot better in speed than MOSIC. And in fact, if we keep going and in other problems as well, at some point MOSIC will run out of memory, and Hypatia can keep going and solving more problems. And again, this is primarily thanks to the reduction on size. And again, Chris and Leah worked a lot on actually making the code stable, because even just writing a completely pure vanilla version, it would still be hard to actually beat an advanced code like MOSIC. So not entirely sure how early I am, but I guess it's like this is mostly what I wanted to talk about. So if you want to know more about Hypatia, we have one paper that is available. The repo and an update to the paper and another paper hopefully will come up in the, let's say, next couple of months. I didn't mention Conic optimization at JuMP Developers Workshop #4, which was supposed to happen in June of 2020. It was unfortunately canceled due to COVID as well. So I don't have a lot of examples on Conic. I will say that Yuri Nesterov was scheduled to give a plenary. So I guess Conic was still being sort of front and centered in JuMP developers, in the JuMP developer world. One other thing that I wanted to say is like, if you have interesting applications that we use on JuMP, either academic, real world, anything that where JuMP was useful, we're trying to collect all that information. So please let us know. Please email that to Oscar, his Northwestern email. And finally, one parting thought is like, so one of the things I mentioned, Julia makes you bold. It allows you to try out new things without necessarily diving deep. So for instance, like that's how I basically started learning. I still would not consider myself an expert in continuous optimization, but now it's trying this has allowed me to actually dive deeper in the subject, and it was very interesting. So I would suggest use it as a way of trying out new math and new techniques before you see if it's really worth diving and learning on them. But do dive and learn a little bit more. Don't use it as an excuse just to blindly use the code. Once you're convinced that it works, dive deeper, peel the onion. That's what Julia was designed to do, to peel the onion and go deeper, both in the code and in the math. So with that, thank you very much. It's been hopefully it's been somewhat instructive, and I'll make sure the slides are up somewhere so you can follow the links if you want to learn more about any other topics. So thank you.
Thank you, Juan Pablo. We've got a couple of questions from the Discord chat. The first one was, how do you feel about how macro heavy / DSL like JuMP is?
So basically, that's an interesting thing that, so in essence, this is like, I would say it's somewhat of a deep question of what are the right oracles for optimization? And the more natural oracle is functions. Functions are mathematical objects and functions are programming language objects. And that's a very, very one-to-one. In conic optimization, for instance, the objects are sets. So it's a little bit harder. There's not a one-to-one. And that's why you actually need a little bit of a DSL. There's the affine part, which is an affine function, and that you could potentially integrate it more. But you really get to the stage of function when you go to the barriers. So in some sense, there's an issue there is like, it's hard to really make the belongs to match between the math and the Julia code. And I would say that's the reason why you need this extra DSL on top of the code. So it's in some sense, at least that belongs, it will be somewhat necessary to have it in some way, potentially as a DSL. Maybe there's an interesting solution, but I would say that's the crux of the problem.
That makes sense. Referencing, I think one of the slides, maybe 4 or 5 slides ago, the question was, how general is the cone here? Are positive semi-definite matrices a cone? Are polynomials positive on index 0, 1 a cone here?
Yes, so it could be very, very general. So I guess like a polynomial, what was the polynomials? So I guess non-negative polynomials, for instance, would be a cone. It's like infinite dimensional, so I guess you would need to restrict it in some way. If you have a positive semi-definite matrix and you want them to coefficients to be non-negative, you could intersect it with the positive definite cone with the non-negative variables. And again, you can combine cones, or you could find a better barrier for that particular cone. And if you can find a better barrier that satisfies all the properties, you could plug it in. So you could really go crazy with the hard part of being able to put the cone is really getting the logarithmic homogeneous self-concordant barrier for the cone. That's where the hard mark would be. But besides that, you just want it to be a convex cone that is closed. And that's about it.
Awesome. And really quickly, the closing question that I have for you, are there any key features or hurdles that the JuMP team that you all are trying to overcome before doing a 1.0 release of JuMP?
Very good. I guess I would attribute it to the, I would expect that if we actually had the JuMP developers workshop, we would probably be at 1.0. So I won't claim this is anything official, but it's we're close. It's the distance has been, so I think I almost always say this every time I talk at a JuliaCon. I say by the end of the year, but I'm gonna say it again. Let's say by the end of the year. Hopefully it'll be a little bit earlier.
Awesome. Well, thank you. I appreciate your time today, and everyone join me in thanking Juan Pablo for this awesome talk.
Thank you very much.